Projective Geometry, Volume 1, by Oswald Veblen and John Wesley Young.
Chapter 6, Algebra of Points and One-Dimensional Coordinate Systems. Section 57, Coordinates in a Net of Rationality on a Line. We now consider the numbers associated with the points of a net of rationality on a line. The connection between the developments of this chapter and the notion of a linear net of rationality is contained in the following theorem. Theorem 14. The coordinates of the points of a net of rationality R of P0, P1, P infinity form a number system, or field, which consists of all numbers, each of which can be obtained by a finite number of rational algebraic operations on 0 and 1, and only these. Assumptions A and E. Prove by Theorem 14, Chapter 4, the linear net is a line of the rational space constituted by the points of a three-dimensional net of rationality. By Theorem 20, Chapter 4, this three-dimensional net is a properly projective space. Hence, by Theorem 10 of the present chapter, the numbers associated with R of 0, 1, infinity form a field. All the numbers obtainable from 0 and 1 by the operations of addition, subtraction, multiplication, and division are in R of 0, 1, infinity. Because, by Theorem 9 of Chapter 4, whenever x and y are in R of 0, 1, infinity, the quadrangular sets determining x plus y, xy, x minus y, x divided by y, have 5 out of 6 elements in R 0, 1, infinity. On the other hand, every number of R 0, 1, infinity can be obtained by a finite number of these operations. This follows from the fact that the harmonic conjugate of any point A in R 0, 1, infinity with respect to two others, BC, can be obtained by a finite number of rational operations on A, B, C. This fact is a consequence of Theorem 13, Corollary 2, which shows that x is connected with a, b, c by the relation the quantity x minus b times the quantity a minus c plus the quantity x minus c times the quantity a minus b is equal to 0. Solving this equation for x, we have x is equal to minus 2bc minus ab minus ac all divided by 2a minus b minus c. A number which is clearly the result of a finite number of rational operations on A, B, C. This completes the proof of the theorem. We have here the reason for the term net of rationality. Footnote: the expression for x cannot be indeterminate unless B is equal to C. It is well to recall at this point that our assumptions are not yet sufficient to identify the numbers associated with a net of rationality with the system of all ordinary rational numbers. We need only recall the example of the miniature geometry described in the introduction, section 2, which contained only 3 points on a line. If in that triple system geometry we perform the construction of the number 1 plus 1 on any line in which we have assigned the numbers 0, 1, infinity to the 3 points of the line in any way, it will be found that this construction yields the point 0. This is due to the fact previously noted that in that geometry, the diagonal points of a complete quadrangle are collinear. In every geometry to which assumptions A, E, and P apply, we may construct the points 1 plus 1, 1 plus 1 plus 1, ... thus performing a sequence of points which, with the usual notation for these sums, we may denote by 0, 1, 2, 3, 4, ... Two possibilities then present themselves. Either the points thus obtained are all distinct, in which case the net, R 0, 1, infinity, contains all the ordinary rational numbers, or some point of this sequence coincides with one of the preceding points of the sequence, in which case the number of points in a net of rationality is finite. We shall consider this situation in detail in a later chapter, and will then add further assumptions. Here it should be emphasized that our results hitherto, and all subsequent results depending only on assumptions A, E, and P, are valid not only in the ordinary real or complex geometries, but in a more general case of spaces. which are characterized merely by the fact that the coordinates of the points on a line are the numbers of a field, finite or infinite.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.